In this video, I'm going to talk about DeMorgans Law. DeMorgan was an actual guy who came up with this rule for distributing a not statement over a Boolean expression, either an or expression or an and expression. So let's talk about what the rule is, and then I'll prove to you that in fact it works. So the rule says that if you have a not outside of a Boolean expression, if you want to distribute that not, you must change everything inside the expression. So as I distribute this not, instead of a being equal to 10, I have an a not equal to 10. I'm distributing it to the or becomes an and I know this is a little bit funny to students sometimes. When I distribute it to this last part of the expression, the b equals 10 becomes b not equal to 10. And we can prove that these two expressions are logically equivalent by running them on every possible combination of a equals 10 or not, and b equals 10 or not equal to 10. So let's just run it on this first case here, and we can see that at least they're logically equivalent now when I have a as some value that's not 10 and b equals 10. And we could actually try a bunch more values. Let's make a and b both equal to 10 and see if we get the same value, the logical equivalent value for both. Yes, they're still both false. Now let's make them both not equal to 10 and run it one more time and see what we get. And we get true. So in fact, they do seem to be logically equivalent. And if you think about it for a moment, I think you can see why here. This first statement is only going to give you a true if both parts of the or are false, making the or statement false, and notting it makes it true, right? An or statement is only false if both parts are false. So this is like, I have basically, it's not true that a equals 10 or b equals 10. It's the same thing as saying a not equal to 10 and b not equal to 10. Yeah, that makes sense. This and statement is only true if both of these parts are true. Yeah, give it a little bit more thought. I think you'll see that these are logically equivalent. All right, let's do one with an and. This a little bit trickier. So if I start out with an and statement, and I'm going to make this maybe a not equal to 10. Oh, yeah. So, and I'm going to ask you to pause the video maybe in just a moment here. I want to know what statement would be logically equivalent to this statement here. In other words, what would happen if I distribute this not? Giving it some thought? All right. You got it? I'll give you the answer. So I have a not equal to 10, right? The a equals 10 becomes not equal. The and, that changes also, becomes an or. And the b not equal to 10, I have to negate that also. That becomes a b equals 10. So these two statements are logically equivalent. We can run them on a bunch of values and prove that that's the case. In this case, they're both true. Oh, I don't know. Let's make these both 10. That's very exciting. And let's see what we get here. They're both true. Also, what haven't we tried? Let's make, I think we haven't tried this, perhaps? I forget. I don't know. if that, let's see. And they're both false. So I think we tried every possible combination, I think. Anyway, these are logically equivalent. All right, we're going to do a couple more, so hang in there. So here I have a Boolean expression with, again, a not outside of this or expression. So how would I distribute this not? Well, you can pause the video if you want for a moment and see if you can work it out. You got it? All right, so I'm going to do it. So as you know, DeMorgans Law tells us that when you distribute a not, everything inside the parentheses must change. So instead of a being greater than 10, well, what's the opposite of that? Well, if a is not greater than 10, a must be less than or equal to 10. To 10, sorry. I'm distributing the not to an or. That must become an and b not equal to 10, well, what's the opposite of that? Well, that must be b equal 10. So those statements must be logically equivalent. And if we run them, we could try a bunch of different values for a and b, and you'll see that they are going to be the same. In this case, they're both true. Let's make one of these values false, just to make sure that we get the same values here. They're still both true. Let's make them both, a and b, both not 10 now. And let's see if we get the same values again. They're both false. And we could try different values for a and b, and you would see that these are logically equivalent. All right, we're going to do one more. In this example, I made a and b Boolean values, and I set a to false and b to true. So Let's see. Actually, if I ran this already, so this Boolean expression actually gave me a true. And this is a little, you can kind of think through this on your own, but it should make sense to you why this must be true. Actually, let's talk about it. Because if A is false, so this first part is false, and not B, so B is true, not B would be false. I have false and false, which of course is false, and then I have a not on the outside, which makes it true. So my question to you, and of course you're going to pause the video, I'm sure, and give it a try, is how would I distribute this not into this Boolean expression, this inside Boolean expression? All right, if you got it, well, you know the rules now. I have to negate everything. So instead of this being A, it would have to be a not A. Instead of this being an and, it must be an or. Instead of this being a not B, it must be a B. And this is an equivalent Boolean expression. And we can run it just to make sure that, in fact, it is. And they're both true. And again, we could try different values. We could make them both true. You have to actually spell the thing right. We could make them both true and rerun it. And you would see that we will get the same exact value. Let's make them both false. I have to get better at typing, you know. All right, let's make them both false and run it one more time. And again, we can see that they're logically equivalent in every single case. Now, what's one that we didn't try? I don't think we tried false true yet, did we? Maybe we didn't try that. Let's see if we get the same value for this. They're both true. I think we've gotten both true for all of them. I wonder if I can make it. I don't think they've ever come up as false. So how could we actually get this to come up as false? I think we would need this first expression to be true. So A would have to be true. And B would have to be false. And then I think we're going to get a false here. So let's try that. They both should be false, and they are. They are both logically equivalent. All right, you have a few to practice, and thanks so much for watching.